So, welcome to the session today. We will be learning about the lateral earth pressure today. And I'll be using, I'm finding the lecture note. Give me 1 minute. So, is there any questions from the previous day? No questions. So, I have uploaded the assignments so that you will be able to submit them as soon as possible, and the deadline would be the December 15th, though, as I can remember. So what I'm doing is here is I'm making that editable lecture note, therefore it will be easy to explain. Yes, I have few more pages. Give me a minute. Just 1 minute is enough, I think. So today what we are going to do is we are going to learn the lateral earth pressure, that is right, done. Let me share the screen. Right, today we are talking about the lateral earth pressure, and then we will move to the the retaining walls. You will be designing a retaining wall, most probably today or in the next week. Right, you might have seen so many lateral the retaining structures like this. So what we are going to calculate is, we are going to calculate the lateral forces acting on these vertical or retaining structures. The basic idea or the basic requirement of this kind of retaining structures is to retain a particular amount of soil or soil retaining structures. So here you can see this soil amount, this soil column or soil part is being retained by this particular structure. So here by this structure, this soil is this side soil is retained. So this kind of huge structures are also there. So these are also can be taken as retaining structures. Now what we are doing is we are going to find the lateral earth pressure on these structures, right? So there are so many other uh, so many other structures. So this kind of, I mean, in the idealization, so you can take this kind of cantilever retaining walls, the braced excavation like this. Now what we do is we brace this, and there will be lateral forces from this particular soil towards these plates. So then anchored sheet piles or sheet piles, right? So likewise, there are so many applications of the lateral supports or lateral forces, and we have to estimate the lateral soil pressures acting on these structures. So if we have a gravity retaining wall to retain this soil amount, then we have to determine the lateral forces acting on this particular structure. So we are going to determine these lateral forces acting on this particular structure. And during the soil nailing also, we have to decide what are the lateral forces acting on this particular structure. And reinforced earth wall also, the lateral structure, so the lateral forces will be resisted by these reinforcements. Right? We have to design these reinforcements so that the structure can withstand against the lateral forces. So as you can see, the soil nailing and the sheet piles marked for driving. Now when you drive sheet piles, and you can see sheet pile wall here and retaining wall here made with wooden and steel, and the reinforced earth walls are increasingly becoming popular. So you can see this kind of reinforced earth walls in highways or expressway embankments. So what you can see is something like this, but inside you have the geosynthetics. What you can see here is this beautiful surface, but inside this one they have included these geosynthetics and the crib walls. So that is something like this. The cribs were interlocked between each other with the stretchers and headers, and that is filled with the soil. And good drainage and allow plant growth, and so you can see how the plants have been grown. Right? So what is the purpose of this having this kind of wall? Now one of the purpose would be retaining wall to support the fill. Now the initial surface is something like this. Initial actual ground surface is something like this. So if you need to have some surface like this, some fill, this green color fill, if someone needs to if you need to have some fill like this, something like this, right? What you can do is you can construct a retaining wall here and fill this, so that there will be a lateral horizontal force acting on this particular structure, so that we have to know about these values in order to determine uh, the size, or in order to design this particular structure. Likewise, if we need to cut this kind of a cut, if we need to remove this particular soil, then we need to know the lateral earth pressure acting on this, something like this. Right? If you have anything to note down, please note them down. then there is a particular difference between the soil pressure and the water pressure, right? What I'm going to now what I'm going to teach you is this difference. Now let's take this word isotropic. The meaning of this isotropic is the properties are same in every direction. The properties are same in every direction. Now consider the hydrostatic pressure, the water pressure. As Archimedes has found, the water pressure is equal in every direction. The same value, ne? This way, this way, this way, this way, everywhere it is same. But so anisotropic material, they are not like that. So isotropic means the properties are same in all directions. But anisotropic materials, the properties vary in the direction, right? So we will take the vertical stress as sigma z. I will delete this blue color one so that it will be easy, right? So this vertical stress is not equal to the horizontal stress, right? This vertical stress is not equal to the horizontal stress. However, the vertical stress is greater than the horizontal stress. The vertical stress is greater than the horizontal stress. So this kind of materials are called as anisotropic materials. Now as an example, if you consider another material, let's take pencil. You get a pencil, you can see through, no, not a pencil. I have to show that then. Okay. However, the isotropic materials means the properties are same in every direction, but the anisotropic materials, the properties are different. So the soil pressure is an anisotropic property, right? In the soil, the properties, these vertical and horizontal stresses are different, but in water, the horizontal and vertical stresses are same, that is the water pressure. Now the problem is soil has both solid and water. So for the dry soil, we have to do this anisotropic analysis, and for the water, we have to do the isotropic analysis. Right? Therefore, when considering the soil, you have to take the dry soil and water separately. Dry soil and water separately. So first we will discuss on how we can find the earth pressure at rest. Right Now let's consider a point like this. Before that, I will give you few minutes to write this down. Right, any problem? Any questions? No. Right, then we will move to the earth pressure at rest. Now basically this is divided into three parts. First we will see the earth pressure at rest. That means when we are dead, what happens is when we are dead, we are buried inside the soil. We are buried inside the soil. So the what is the lateral pressure acting on us? So this is something like that. What is the lateral pressure acting on us? So if we are buried, the vertical pressure will be sigma dash V, right? Vertical effective stress. This will be the vertical effective stress. Now please keep in mind that there are two stresses, that is total stress and the effective stress. How you can find the effective stress? Actually, I have explained you in the previous uh, previous week or something like that. The effective stress equals total stress minus pore water pressure, right? The effective stress equals total stress minus pore water pressure. These are the effective stresses, right? This is an effective stress, right? So how you can find this effective stress? This effective vertical stress is total stress at this particular point minus pore water pressure. And what this theory says, the ratio between this sigma dash h divided by sigma dash v, that is the vertical effective stress is sigma dash v, this sigma dash h is horizontal effective stress. So what this says, horizontal effective stress divided by vertical effective stress is a constant, and that is known as the coefficient of lateral earth pressure. That is called as coefficient of lateral earth pressure, and that is called, that is K naught, that is at rest. Now this is at rest, so it is the coefficient of lateral earth pressure at rest. That is the coefficient of lateral earth pressure at rest. So you know how to find this effective stress, total stress minus pore water pressure, and how you can find this sigma dash h. Now if you know this K naught, so that this divided by this book will be K naught, so sigma dash h can be found by K naught times sigma dash v. Right, we will be doing them later. Okay, if you need to write down anything, you can write down. Right. Then this is how you can find this K naught. How you can find this K naught is for the normally consolidated clay, K naught would be 1 minus sine phi dash. Phi dash is the friction angle, effective friction angle. The friction angle in terms of effective stress, right? That is phi dash. So if you know the effective friction angle, then you can ignore. Can we convert this into PDF? Then it would be easy. So yes, if you have if you know this sigma dash v, if we consider this particular point, then sigma dash v is the effective total stress, total effective stress. Sorry, effective vertical effective stress. So you can find the vertical effective stress and multiply it by K naught. If you know the sigma dash value, that is the effective friction angle, then you will be able to find this K naught. If you know K naught, then you can find this sigma dash h. That is for the normally consolidated clays. Or in most of the cases we find this one. But for the over consolidated clays, you can find K naught something like this. Right? I'm not going to bury the name. For this one, right? This will be an example question. Right. Fine. For example, calculate the lateral total stress sigma dash sigma x at z at this point. If k naught is 0.5, right? K naught value is given, right? Shall we give a try? Before that, if you need any time, you can write this. Right, then we will move to this example. The ground level is there. The S means degree of saturation, and yep. Oh, sorry. Right, shall we give a try? If you have any questions, please ask. Right, I'll give you just 5 or 10 minutes. Yes, but here the friction angle is not given. The reason is they have given the K naught value. So you can directly get this K naught value, but the problem is gamma is not given. So first you have to determine the unit weight. When you determine the unit weight, you can use this equation. This is the very basic equation with the degree of saturation, void ratio, and the specific gravity and the unit weight. So from this equation, you can take first you can determine the void ratio. Void ratio is S equals WGS. Void ratio, S means the degree of saturation, E means the void ratio. But in a normal question, gamma will be directly given, right? I mean, to have some revision or to remind these equations, which you will learn in the soil mechanics subject. I just give in this thing it is included. E means WGS divided by degree of saturation. W means the moisture content. Moisture content is given as 0.3, and specific gravity of some the soil is taken as 2.7, so that you can find the gamma or the unit weight of this particular soil. Right? First, you have to determine the unit weight of this particular soil, but in the normal questions, it will be given. Right, then we can find the saturated moisture, saturated unit weight, because this is the what is given here. I mean the unit weight of this particular soil. In the using the same equation, you can determine the saturated unit weight. Right, then what we can do is we can find the total stress at this particular point. How you can find the total stress is the total stress, that is sigma z at this point, the gamma h value of this particular this particular region plus this particular region. The gamma h or rho g h, the same thing. Rho g means gamma. The gamma h of this one means gamma would be this 14.6. 14.6 times h should be 2 times 14.6 plus 3 times gamma saturated. So you will get this one, and the total stress would be 82.6 at this particular point. That is the vertical total stress, total vertical stress, right? Then we can find the effective stress. Before finding the effective stress, you will have to find the pore water pressure at this particular point. Pore water pressure means gamma W H. H is 3 meters. From here to here, it is 3 meters. 3 meters multiplied by gamma W, that would be 3 times. 3 times 9.8, that is 29.4. So you have the total stress at this point, total vertical stress at this point, and the pore water pressure at this time, at this point. Now, if you consider the pore water pressure is isotropic. Right? Pore water pressure is isotropic. That means the same pore water pressure acts at every direction. But if you consider the total stress is different. Sorry, if you consider the horizontal stress, that is anisotropic. So first we have to determine the effective stress at this particular point. It is this one. So then using this equation, sigma dash h can be found by multiplying sigma dash v with k naught. So this is the effective horizontal stress. But what they ask is the total lateral stress. Now this is effective stress, effective horizontal stress, right? But what you need is the total horizontal stress, so that you will have to apply or add the pore water pressure. The reason is the pore water pressure does not have any components, but the lateral earth pressure, the soil has components. Components means the vertical stress and the horizontal stresses are different. But water, it is not like that. So any questions? Yes, you can ask any questions. Any question? No? Right. If you don't have any questions, we will move to the next one. Then active and passive earth pressures in granular soils. So we will consider a smooth wall like this. We will consider a smooth wall like this. So due to this pressure, what happens is this wall this wall moves towards the soil, and at this side the soil gets compressed. So it is called as passive side. Here in this side, the soil gets released or relaxed. So that is called as active side. Right. So therefore the side which the soil gets relaxed, that is called as active side, and this other one is called as passive side. So if you need to note down anything, you can. Okay, then now this side is the active side, and passive side, the movement is the other way. So we will be talking about an equation. That equation is same: sigma v divided by sigma h, sigma v dash divided by sigma h dash is constant. So these are somewhat complex theories, not complex, that is not relevant to you. However, this is what we need. This sigma dash h, that is the effective horizontal stress, is equal to the active earth pressure, the coefficient of active earth pressure. Now, since Rankine has found this one as an honor to him, this is called as Rankine's coefficient of active earth pressure. Rankine's theory means that one. Rankine's coefficient of active earth pressure. And how you can find the Ka is 1 minus sine phi, it should be phi dash, right? 1 minus sine phi dash divided by 1 plus sine phi dash. Or else you can simplify this equation into tan squared for something like this also. So this is the basic of the active earth pressure. Right, then so these are the failure planes, and there is not that much important. So this is regarding the granular soils. Granular soils means cohesion is zero, but when you have the cohesion for the cohesive soils, you have some component, cohesion component. So that becomes, this becomes the equation. I mean, minus 2c square root of Ka. So when you have a cohesive soil with the cohesion, this equation differs. So for the cohesive soils in active earth pressure, this is the equation. Ka does, the equation for the Ka does not vary. So you can write down this one also. Then we will move to the passive earth pressure. First we will see them for the granular soils, that is C equals 0, and that equation becomes like this. For the granular soils, if the cohesion is 0, this is same. and Kp equals 1 plus sine phi divided by 1 minus sine phi. The reciprocal of Ka. Reciprocal means you change the denominator and the numerator. This is for the cohesionless soils, so the granular soils. For the cohesive soils, again that equation is somewhat different. Now earlier it was minus 2c Ka, square root of Ka. Now for the cohesive soils, this becomes the same equation plus 2c times square root of Kp. This becomes plus, right? Negative becomes minus. Sorry. Earlier the negative sign has become plus sign and Ka has become Kp. Now this is for the cohesive soils, that is with the cohesion value. The same equation, if this C becomes 0, if this C becomes 0, you can get the earlier equation. Right. So this is what happens. Active pressure comes from here, and you can draw a triangle here, and the passive pressure comes from here. So we will be learning of those things later. Later means uh, we will do some example. So this is the summary. Coefficient of lateral earth pressure at rest. At rest, that is K naught equals the vertical divided by horizontal, and K naught value for the normal consolidated soil, that is 1 minus sine phi dash, and for the over consolidated soils that becomes something like this. Over consolidated ratio is OCR, and active earth pressure, the equation becomes like this, and the reciprocal is this. And basically you have two equations. Before that you can write this as a summary. sorry. Now, the Rankine surface pressure theory means this one. When the cohesion is becomes zero, then you can remove these two parts in the active pressure and passive pressure. This is the These are the equations that we learned, and there are two assumptions. This is applied only for a smooth and vertical wall, right? We assume that the wall is smooth and the wall is vertical. So this is the theory part, and we will do an example. First, write this one as a summary. Then we have something called the depth of tensile crack. Now, what happens here is when you when this sigma dash is zero at this top point. Before that, I will explain these two. When you when you represent these two parts, what you can do is you can draw this one and this one separately. This one and this one separately. So this triangle would represent the sigma dash Ka part, and this would be a constant throughout the depth. Right? 2c square root K will be a constant. So the resultant of these two, now this is minus now. So the resultant would be at the top point. Sometimes we don't have vertical stress. So this should be minus, right? Did you understand? This 0 minus something, that will be minus. At a particular depth, this value, this positive value, and this negative value, this positive value and this negative value would be 0. So this depth is called as the critical depth. So depth to tensile crack, the tensile depth, or the tensile depth to tensile crack. We can remove this by having a surcharge. We will discuss them later. Then this can be found. Now this is the equation, and you can we can assume that at the depth of ZC, critical depth or depth of tension crack, at the depth of ZC, this would be 0. This would be 0 means the lateral pressure would be 0 at this point. So if you use clay soil, then what happens is there will be tension cracks on top of the retaining wall in the active side. So what we do is we can find the ZC, then we can apply a surcharge, or what we can do is we can have some cohesionless soils, something like granular soil without cohesion, right? Okay, now this is how we can find the depth of tensile crack. You will need this one, so it is better if you can write. Right. We will do this example. So just give a try. Just read the question and give a try. I will explain later. After you give a try, I will explain, right? A 6-meter high retaining wall is to support a soil with unit weight of gamma is given, soil friction angle is given, and cohesion. Determine the Rankine active force per unit length of the wall before and after tensile crack occurs. And determine the line of action of the resultant force in both cases, right? Now, since phi dash is 26 degrees, so you can find Ka and Kp. No. Active side. So it is enough to have the coefficient of lateral earth pressure in the active side. So you can use 1 minus sine phi divided by 1 plus sine phi or this equation. So you will end up with this 0.39. Then square root of k is also found. So sigma dash A can be written in terms of the depth. The depth is h. So sigma dash A, that means active side lateral earth pressure is gamma h Ka, that is this sigma dash vertical, effective vertical stress is gamma h times Ka minus 2c dash square root of Ka. So with the depth it varies. Now with the depth this varies or this increases, right? So you can represent this part. You can represent this part by this diagram and this part from this diagram. Right. Come up to this point. Right. Then we will see at z equals 0, that means at this place, at z equals 0, at this place, sigma dash A becomes minus. So this value is a minus value. At z equals 6 meters, that is at this depth, at z equals 6 meters, so this becomes, this part is the, I mean this sigma naught dash Ka, this minus this minus this, it would be this one. When you substitute the values, it will be 22.77. So you will get a value like this. So active force before the tension crack appeared. This active force before the tension crack appeared. So you can find it using this triangle. The area of any pressure diagram gives us the relevant force. So if you need this active force, you can take the area of this one minus this. So you can determine this active force before the tension crack appeared. This is the area. Area means half times this height times this base. Oh, this is this base times height. So that is what is here. Just come up to that point, and I will explain you how to find the line of action. So here the basic theory was the area of a any area of any pressure diagram or stress diagram is or gives the relevant force per unit length. The area of any pressure diagram gives us the relevant force per unit length. That means this area gives us the relevant force per unit length. And the next one, line of action of a resultant can be determined by taking the moment of area of the pressure diagrams about the bottom of the wall. So the line of action, this is A level, right? But you have learned in A levels. The line of action of that particular force is given by the centroid of the pressure diagram. If it is a triangle, then that would be 2/3 like that. So this is the basic of your the theory. So it is better if you can write down this one. So based on this theory, we can get the line of action of the resultant force. Right. So and using that the equation for the depth to tensile crack, you can get the depth to the tensile crack. Right. Please come up to this point, and this is somewhat complex situation, but we will be doing some simple calculations. So the next topic is the retaining walls and brace cuts. So we will move to the retaining walls after having a small break of 10 minutes. So we can have a break about 10 minutes and we will move to the, what is it, retaining walls. Let's meet at 2:40. So we will be talking about this retaining walls. Did I unmute? Yes. We will be talking about this retaining walls and braced cards. So basically there are four types of retaining walls. The first one is gravity retaining wall, and the next one, second one is semi-gravity retaining walls, and the cantilever retaining walls and counterfort retaining walls. This is Braja M. Das book, right? Wait, I will show you the first cover page. This book, Fundamentals of Geotechnical Engineering by Braja M. Das. I think I have shared the PDF with you. Yeah, the in chapter number 13. Right, gravity retaining walls. Gravity retaining walls. Now, this is the gravity retaining wall, and this is called semi-gravity retaining wall. Semi-gravity means there's a reinforcement part. There's a reinforcement part, and a cantilever wall. The section is very much thin compared to gravity wall, and the cantilever action is applied here. And this is the counterfort wall. There are counterforts. These are called as counterforts. So these are the types of retaining walls. Uh, Sometimes there might be questions asking what are the types of retaining walls. So I will give you 1 minute to write down these types of walls, types of retaining walls. Right. Then we will be yes, I think these dimensions are a little bit not clear. However, if we take the total height as h, if this total height as h, then there are some ratios. So this toe can be 0.12 h, and this height is 0.12 h, something like that. There are some basic ratios. So, however, we don't need those things. Sometimes there might be a clear picture of the, not sometimes, that is clear in the original book. I have the original book at my home. So in the original book there are the ratios are there. It means if this is h, so that you can select this depth, this length, and etc. So however, what we are doing here is the designing of this kind of retaining wall. So the first thing is we have to apply these lateral earth pressure theories into the design. So if we can assume that this is the retaining wall, so this is the retaining wall, and there is a particular amount of soil in the active side that is taken as WS, and we assume a vertical and a smooth plane AB. vertical and smooth plane AB, and we apply the Rankine's earth pressure theory to that particular plane AB. The unit weight, friction angle, and cohesion value in the active side can be given, and this is taken as H dash. So this is H. And in the passive side, that will be gamma 2 and some other values. So this is how you can idealize that one. And in a gravity wall, the same thing happens. So basically what we check is, we check for the overturning and sliding and bearing. So using this equation, we can find the passive force, or else we can remove the, we can neglect that passive force also. So the factor of safety against overturning can be found like this. This is sigma mr and sigma mo. Sigma mr is the sum of moments tending to resist overturning about point C, and mo means overturn about the sum of the moments of forces tending to overturn about point C. Right? We will see what this is. Now, if you consider this one, now this one, this moment around this point is the resisting, no, this point we take the moments around this point, right? I think that might be there in the next page. Yes, if we take moments around this point, the weight due to this soil, the soil weight is a resistant moment. So that will be a resisting moment, and this passive force will be a resisting moment, and this active force, this moment, the moment by this active force, that will be tending to overturn this, and the weight of this structure will also be the resisting moments, right? So likewise, we have to analyze those things, and the overturning moment is the horizontal force, or due to this one, this will overturn, right? Yes, I think the passive force, so you can write down anything that you need here. So then if it is a gravity retaining wall like this, the same thing happens. So it is better if we can go for a what is it? Go for an example. So this is the example. Thought that there would be numbers here, but why is that? Yes, here it is. So we will move to this example, then only we will learn this one. So this is the example. Could you please draw this one with these numbers? Otherwise we will miss the picture. So here what happens is this divided into several sections, right? This one is now, first of all, what happens is now we are considering a 1 meter length, right? We are considering a 1 meter length to the other side, towards the lengthy side. We are considering 1 meter length, and this first rectangle, this is the number 1, section number 1, and this triangle would be 2. That one triangle means this triangle times 1 meter length there, right? There is a length to 1 meter. Now this rectangle times 1 meter length towards the other, towards the 3D side, and section 3 is again a rectangle. Section 4 again a rectangle, and 5 is a small triangle. So whole the dimension is divided into some simplified sections or simplified shapes, so that we can find the we can easily find the area and the line of action or the centroid. So when you select the triangles and rectangles, then it is very easy to determine the area and the centroid, or the length to the centroid. And the gamma, c, phi, every value is given. Right, everything is given there. Right, now what you can do is, first you can find this total height, this small height. So from here to here it is given as 6 meters. From here to here it is 6 meters. So this would be 6 and this would be 2.6. So based on this 2.6, you can determine this one, 2.6 tan this angle. This angle is 10. So this small height h1 would be 2.6 tan 10. That will be 0.4458. So we are applying Rankin's theory to this particular shape, this particular vertical and smooth plane. We are applying the Rankin's theory from this point to this point, that is h1, h2, h3, this total height. We are applying the Rankin's theory to this total height. That is total height. Right, that is what we are going to do. And first we will find the active lateral force. You can directly get this equation since the cohesion is 0. Since the cohesion is 0, you will not get that 2c square root of ka part. So there would be a triangle here, only the triangle part, and the rectangle would not be there. Yes, first of all you can find this total length, and we can tell that we will assume this. You can mark this as a, this point as a, and the bottom point as b. We will apply the Rankin's theorem from this a to b, assuming that this is a vertical and smooth plane. Then we will apply Rankin's theorem from A to B, assuming AB is vertical and smooth. Right? This is very important because based on this assumption, we apply this this equation. So you can write this one, and yep, you can do this calculation first. If you have any questions, please ask. Right? Then what we can do is, then we can prepare, sorry, before that we can find the Rankine's active force per unit length. So when you directly find the force, you can take this equation, that is half times, they have directly taken this equation, the area of this triangle, the area of this triangle. So they have directly taken this triangle. The area of this triangle means half times height times base. Half times this means if you apply the sigma naught dash as gamma h. Oh, they don't have it. Gihani Nimeshika. Yeah, I have this. Gihani Nimeshika has joined. I think you might have outside Lincoln University, Sri Lanka joined. Gihani might have joined here using her some other email address. That is why that tontong sound came, right? Right here. I mean, if you if you join using the Lincoln email address, then there's no point, there's no any problem. Otherwise, I will have to admit it. Right. This area becomes half times h times this sigma naught dash k. Instead of this sigma naught dash, I can put gamma h, because sigma naught dash is the effective stress. So this will be gamma h. Then the equation becomes this one. Right? Half times gamma h squared k. Half times h times this, half times this times this times. Oh yes, that is it. So that is what they have taken here, half times gamma h squared. However, h dash squared is this total height. So they have, first they have taken the passive force as 161.4. Then this is the passive force. That passive force is parallel to this plane, the horizontal, sorry, the top surface. So that is the theory. Always this passive force is parallel to the top surface. So this is parallel. So this PA can be resolved in the horizontal and vertical direction. This PA can be resolved in the horizontal and vertical directions. So that is how they have done this one. So please come up to this point, and if there is anything anywhere you can need the clarifications, please ask. Right? You can find this Ka by 1 minus sine phi divided by 1 plus sine phi, because sine phi values are given. 1 minus sine, this one, 1 minus sine 30 divided by 1 plus sine 30. So here that is based on table 11.2. Based on this table, they have taken this as 0.35. Right, any questions? So then we can prepare a table like this to determine the factor of safety against overturn. The following table can now be prepared to determine the resisting moment. So in this first column, you have the section number, then area, weight per unit length, then moment arm from point C and the moment. So we prepare a table like this. I will explain how you can get these values. First have a table like this so that I will explain one by one. So the first column is section. Section means 1, 2, 3, 4, 5. The sections that we have selected 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The number of sections might vary depending on the geometry. If this is just a rectangle, then two not will be in there. Then area. So section number will be just a rectangle, and section 2 will be a triangle, and section 3 will be a rectangle, triangle. So by looking at this one, you can put the areas. I will just explain area and the weight per unit length. Now we are considering the 1 meter to the other side. So weight can be taken by this. We have the volume now because in the other side we have 1 meter. If you multiply this by 1 meter, then you have the volume. The volume multiplied by the unit weight would be kilonewton. Then kilonewton per meter cubes multiplied by this volume. This is multiplied by 1 meter would be volume. Then this would be the weight per unit length. Then when you multiply this 3 by the unit weight of concrete, this one multiplied by the unit weight of concrete, that would be 70, 24, something like that. So likewise, these areas can be multiplied by the unit weights of concrete or soil. Then you will get this value. And the moment arm is the distance from C, distance to the line of action. Now the weight of this one, section 1, is towards like this. From C to this, the from C to the perpendicular length from C to the line of action of the weight of the one, section 1, that would be this 1.15. So likewise, you can mark all the values and you can take the weight times the moment arm, you will get the moment. So likewise, please fill these values. Don't copy these values, just try to do it alone, right? So if you have any questions, please ask. Right? So any questions? So if you have finished, this will be the total vertical weight. So if you add this total weight, you will get the total vertical weight, the total vertical force. If you add them, that will be this one. And this PV means this PV, the vertical component of the lateral earth pressure. Then you can take the all the moments here. Right? Then this would be sigma mr. So find them also. Here they have assumed the gamma, or the unit weight of concrete, is 23.58. So then we can find the uh, overturning moment by this horizontal force multiplied by the moment arm. Horizontal force would be 158.95. That is the horizontal component of the lateral earth pressure. And then h dash would be the total length, and there will be a triangle, therefore one third depth at a triangle. One depth, when you have a triangle like this, you can apply that force, or the force is applied at a one third of the depth. So you will get the m naught as this one. So the factor of safety against the overturning is sigma mr, that is this one, divided by the overturning moment. That would be this one. Therefore, normally if it is greater than 1.5, if it is greater than 2, if it is greater than 2, so we take it as okay. So come up to this point. If you have any questions, please ask, right? You will have to do it alone in the exam, right? So any questions? So then the factor of safety against sliding. So in the numerator, in the denominator, what you have, what you should have is the driving forces or the sliding forces. The only sliding force is PA cos alpha, that is this component PH, the horizontal component, and the resisting forces are at the bottom. The resisting forces are, this is mu r, this is mu. Mu means the frictional force, and delta is taken as k1 sigma 1 dash, and r is the perpendicular reaction or the sigma v total. Then the cohesion, the addition between concrete and soil, the addition between concrete and soil is taken as a portion of the soil cohesion, that is k2 times c2, and it is multiplied by b. B means the width of the retaining wall plus passive force. So in the denominator you have the driving or the sliding force. In the numerator you have the resisting force. So first you have to find the passive force, and then you can find the first find the passive force. To find the passive force you need Kp. Kp means the coefficient of lateral earth pressure in the passive side. Then Kp equals this one, the reciprocal of Ka, and you can find the passive force. Then you can just apply the passive force to this equation. You will get it as 2.73 is greater than 1.5 is okay. So come up to this point. So it will take considerable time to explain the factor of safety against bearing. So we will see. Just come up to this point first. So before finding the factor of safety against overturn, sorry, bearing capacity, first you have to find the eccentricity. So using this equation, you can find this. B by 2, B means 4 meters. If this is not satisfied, then you have to change the dimensions, and again you have to do it. Right? If you have the unsatisfied factors of safety, then you have to do it again. So first you have to find the E value using this equation. So then we can use the ultimate bearing capacity equations that we have learned earlier. So that is how we can find the factor of safety against sliding and overturning. And the time will not be enough to discuss the bearing capacity failure. So we will be discussing it in the next day. So you can use those theories to determine the factor of safety against overturning in this one. These examples, you can try them, right? The same method. Any questions from today's session? That if you don't have any questions, then let's wind up the session today. So please submit your assignments. I think I can't remember the date deadline. I think 15th December or something like that. Let's see. Yes, December 15th. So you can submit them before 15 December. So that's it. Then we will meet in the next week with the factor of safety in the bearing capacity and rest of the things.